Now I will argue that these enhanced multi-tape Turing machines have the same computational power as regular Turing machines. Multi-tape machines certainly don't have less power. By ignoring all but the input tape, we obtain a regular Turing machine. Let's see why multi-tape Turing machines don't have any more power than regular machines. On the left, we have a multi-tape Turing machine in some configuration. And on the right, we have created a corresponding configuration for a single-tape Turing machine. On the single tape, we have the contents of the multiple tapes, with each tape's contents separated by a hash. So here's the first tape, here's the second tape, here's the third tape. Also note these dots here. We are using a trick that we haven't used before, expanding the size of the alphabet. For every symbol in the tape alphabet of the multi-tape machine, we have two symbols on the single-tape machine, one with a dot and one without. We use the mark symbols to indicate that the head of the multi-tape machine would be over this position on the tape. So the 1 is marked here, the 1 is marked here, and the 0 is marked here. Simulating a step of the multi-tape machine with the single-tape version happens in two phases, one for reading and one for writing. First, the single-tape machine simulates the simultaneous reading of the heads of the multi-tape machine by scanning over the input and noting which symbols have marks on them. So here it would first note that 1 is under the head of the first tape, then that another 1 is under the head of the second tape, and then that a 0 is under the head of the third tape. That completes the first phase where we read the symbols. Now we need to update the tape contents and the head positions or markers as part of the writing phase. Let's say that the multi-tape machine changes this 0 to a 1 and moves the head to the left, like so. Then on the single-tape machine, we need to change this 0 dot to a 1 and change this 0 to a 0 dot. Note that it's possible that one of these strings will need to increase its length when the multi-tape writes to a position it hasn't reached before. In that case, we just right-shift the tape contents to allow room for the new symbol to be written. Once all that work is done, we return the head back to the beginning to prepare for the next pass, like so. And notice that I updated the tape contents appropriately. So all the information about the configuration of a multi-tape machine can be captured in a single tape. And it's not too hard to convince yourself that all the logic needed to read from multiple places and remember all that contents in order to figure out the right writing response can also be implemented with a state transition logic. It's a good exercise to work that out if it's not obvious to you.